Okay, you have an exam on Friday, I guess. I haven't seen it. I don't have a clue what's on it. I don't know a thing about it. So, you know, you're on your own on that one. So I'm happy to answer any questions you have today. I came up with a few example problems. We'll go over them real quick. And if you want to talk about something or whatever, just ask. But I just honestly don't know what's on the exam. So, but it's going to be something, you know, on these topics, I presume. So I came up with a couple. Oh God, Thompson only trashed. There it is. He trashes the board and then. Yes.
This practice prelim that I posted, in one of the questions it says like determine Q naught for like a specific cavity, and there are a lot of Q's. It's very confusing. So the Q naught would be like the Z plus I Z naught, which I guess
yeah.
would just be I Z naught.
Yeah. If I'll do it probably. Okay. We'll give you a cavity and we say what's Q. We better tell you where. Because if I give you a cavity and say what's Q in this, well, Q depends on where I'm at. So I would have to say find Q at the waist or find Q in this mirror. So let's do an example.
Okay.
I'll just go to that one right away. So here's a problem. I got two mirrors. One has R equals 50 centimeters. I don't know if you can read that. This is such a messy board. One has R equals 100 centimeters. Where is the waist? Where's the waist in this cavity? So, you know, usually if I have a symmetric cavity, you know it's going to be in the middle. Or if you got a flat mirror, you know it's going to be on that. But here I don't know where it is. So here you have to find Q in this cavity. And once you know Q, you know everything. And I can choose any place I want to find Q. I just have to do a round trip. So what makes it easiest for me in terms of matrix, I'm just going to start, say here, I'm going to do a round trip like that. And do that. Now this is a lot of work to do on an exam. But so you do. So I'm going to propagate 20 centimeters. Oh, I made it 20 centimeters long. So I'm going to propagate 20 centimeters. 1, 20, 0, 1. Then I'm going to hit a 100 centimeter mirror, and it's a curved mirror, so it's going to be 1, 0, minus 2 over 100. That's the mirror. 1 over F or 2 over R. Then I'm going to go another 20 centimeters, and it's 20. It's not minus 20, because I'm writing with the beam. The beam is turned around, so I'm going with it. And then I'm going to hit that mirror. So it's going to be 1, 0, minus 2 over 50, 1. And I'm going to compute that ABCD. So then I'm going to grind this through. Now this is why it's kind of hard in an exam. It's a lot to do on an exam. But that's going to be the ABCD round trip for right here. Right? So I do my round trip. And let's say you've got your calculator all tuned up. You're going to get a matrix like this. 0.6, 32, minus 11 over 250. Obviously, I did this in Mathematica. And minus 17 over 25. Okay, so there's my ABCD for right there. If I did it over here, I'd get a different answer. I'd get a different ABCD. So that's not the right ABCD. That's just the one I chose. Now, from that, I have to figure out what Q is. So we use the ABCD law. And remember, you know, Q in a structure like this has to satisfy the condition that the same Q occurs on a round trip. So I start with a Q here. I do a round trip. I better have the same Q. So here's my round trip. Here's my ABCD law. Q must equal the same Q. And so you mess around with this a bit, and you find that Q equals minus D minus A over 2C plus J times square root of A plus, 1 minus A plus D over 2 squared, all divided by C. So.
Is there a reason you choose the plus J?
Oh, no. I'll choose whichever one's convenient. So you know, it's going to be that. And the reason I chose plus is because usually we define Q is equal to Z plus JZ naught. So I kind of like the positive there.
So wait, so Q,
So all I did here, I just solved, I get the quadratic equation, I solve it. I hope I did it right. And so this is just, CQ squared plus DQ equals AQ plus B, and you just solve it. Okay, so that's where that came from.
why the J though?
Why the J? Because it turned out it was A plus D over 2 minus 1, and then I reversed the order because it was going to be a complex number. And so this will be a real number times J. When you do it, when you actually compute this thing, when you do the quadratic, you're actually going to get, A plus D over 2 squared minus 1. But we know for a stable cavity, this is less than 1. A plus D over 2 has to be less than 1 for a stable cavity. And so this is going to be imaginary. So I just want to, so I flip it so it's not imaginary and put the imaginary term here. Now my calculator doesn't puke when I try to compute this. So I can compute this and I'll get a real number, and I put the J in front. So that's all. I mean, now with Mathematica it's not a problem, but my calculator used to barf. It wouldn't take a square root of a negative number. So anyway, so you do this. You could do this on a desert island now. You're lost, you've been sitting there. What is the Q of this thing? You could derive all these formulas. You don't have to remember some stupid books. This is just simply the quadratic. You derive it. Okay, great. I know A, B, C, and D. I can plug them in. So I do. And when I do that, in this case, you get, what I got was Q was equal to minus 14.54. This was not pretty. Minus 27.7 J. Okay, where's the waste? So I started here. I know Q is minus 14.57 here. So I'm 14.57 this side of the waist. So the waist must be 14.57 centimeters away from that mirror. And that's what Q tells me. Q tells me I'm sitting at Z. Z equals 0 is where the waist is, remember? And so we're 14.5 centimeters in front of it. So we advance along, and that'll put us at the waist. So notice the waist is not in the center, and I've got about another 5.4 centimeters to that mirror there. So the beam is, I should draw this better here. I've got this waist. The beam is spreading kind of like this. So here I've got that mirror, here I've got this one. This is 100 centimeters. This is 50. So it's it's more collimated here. Here's getting more curvy. So it's slightly off center. It's gonna be a bigger beam here, all that kind of stuff. But anyway, it gives you a rough idea what's in the cavity. But I did it just simply by using the ABCD law and the dimensions that were given, and got it. Does that make sense?
So, for Q, normally when you write it like that, you say that the first Q is Q1, and then the other ones are Q.
Yes.
Right.
Okay. So I could have said Q2 and Q1, and then I would have said, in this case, Q2 equals Q1. In a cavity.
Oh, for cavity is different.
In a cavity, yeah, I'm sorry, I should have said that. This is the ABCD law.
Okay.
So I take Q1, it transforms into Q2. But in a cavity, after one round trip, it's got to look exactly like it did before. So that's where the self-consistency situation comes in. So that I assume that. I'm sorry, I should have pointed that out. So here's your ABCD law. We all know and love. This is the condition we apply to a cavity, and then it's just Q equals Q. Yeah.
So does the imaginary component come into play?
Well, that would be my next question. I might say, okay, I found the waist. How big is the waist? So, well, I know the waist is incorporated into the Z naught. And I know Z naught is 27.7. So, I should have been a plus. So knowing that, I know Z naught equals pi omega naught squared over lambda. I have to tell you what the wavelength is. So let's assume it's 1 micron. So you need to know the wavelength. But now I can say, okay, well, the waist then, omega naught, is going to be the square root of Z naught lambda over pi. And Z naught is 27.7 in centimeters. So I better define my wavelength in centimeters. And I'll get omega naught in centimeters. So I just have to be very consistent. So yeah, this does contain information. Whether or not we asked it is another story. But this tells you where it is. This tells you how big it is. So you plug numbers into this. What I got was, not what I get. It was like, oh crap, 290 microns. So a quarter of a millimeter. So you got that's pretty small. Quarter of a millimeter. You look at a pencil lead. You know these half millimeter pencil leads. The diameter of the beam is like that little pencil lead right there. It's a tight little beam. Not a lot of volume in these things. Yeah.
And in a stable cavity, it's impossible for Z naught to be negative, right?
Z naught is always positive. Z naught is really just the size of the beam.
Yeah.
So Z naught's always a positive number. So you always have J plus Z plus J Z naught. I mean, that's a good question. I mean, I can't imagine why it'd ever be negative. I was looking at this silly homework problem you had the other day, and you got a complex C, and I said, this is nonsense. Then I went and looked in Ziegman, there's a whole chapter on complex ABCDs, you know, so who knows, you know, maybe there's something there. But I always Z naught is just keep in mind, Z naught's a real simple, it's basically the area of the beam, you know, so it's always going to be a positive number in my view. I don't know what a negative would be. It'd be hard to imagine you'd get a negative omega, and I don't know what that means.
So there's no physical meaning of an imaginary omega, right?
Not that I can imagine. Yeah. So, yeah, yes?
Can you explain again how you got the beam width? Because the -14.54.
So,
That's negative.
yeah, this is the Q I got. So remember Q is equal to Z plus JZ naught. So the real part of Q is always the distance you are from the beam, from the waist. And the imaginary part of Q is always Z naught.
Oh, okay, so it's negative because you're like at the mirror.
Yeah. So remember, we have this axis here. Here's the Z axis. And wherever the waist is, that defines the zero. Zero is where the waist is. And we don't know where zero is initially. But we do know, when we do the calculation, we get, this is minus 14. Had we done the calculation over here, I should have done it. I'd have gotten a different number. But when you computed Q, I mean, had I done it here, I predict, you can try this, you're probably going to get, I'd be willing to bet Q equals 5.43 plus 27.7J. You're going to get the same Z naught. Z naught's determined by the cavity. The waist is the waist. And this is just going to tell you where you're at. I should have tried. That would have been fun to test. I should have done that just to confirm it. But so you're always going to get inside this cavity, no matter where I try it, I'm always going to get different ABCDs where I go for. But the Z naught should always be the same because the waist is the same. It doesn't matter where I start. And the Z is going to depend on where I start from. Make sense? Okay. So that's how you use ABCDs. They're very, you use this, use this quick calculus, and the thing to remember is that the Q is identical on a round trip. And so then you can go to closed form here and just solve it. All right? So that's a good question for an exam. The only challenge is it's a lot of matrices to calculate. That's always a hassle. So we try to make these things computable. Here was a fun one I thought it would be fun to look at. Since we're talking about the ABCD law. Look at clean board. Okay, so here's a question. I've got a lens. It's got a focal length f. I've got a beam coming along here, and it's got a radius of curvature. So this is beam cruising along, and it's got a radius of curvature here. Let's call it R1. What's the radius of curvature of the field on the other side of the lens? So what does a lens do to the radius of curvature? So let's find out. So I'm going to use ABCDs, and this will kind of show you where the ABCD law found its origin. So let's imagine, let's look at this radius of curvature. I got a bunch of waves coming out. They must have come from a point. You know, they started at some point and originated. So I've got a bunch of rays, and they had to start at one point, and this distance is r away. You know, they're r1 away, right? 1 point. So there's this nice spherical wave out here. Well, let's look at the ray matrix. I've got this ray coming in, and what do I know about it? I know its height, I know R1, and I know its slope, R1 prime, for that ray. So I know an R1 and R1 prime. If I know that, do I know R? Do I know this big R? Yeah, I do. Because it turns out this, this distance here is just, the height. I mean, I've got an angle here. Here's an angle. God, I'll just try this again. Okay. Here's my thing. I'm going up like this. I've got a height. I've got an R, and I've got an R prime. So R equals capital R times R prime. And that's just the sine of theta, or tan theta. So that implies that the radius of curvature is R over R prime. So if I've got points emanating from a source, I've got a point source. This is not true for just any old random ray. But if I got a point source, so all the rays have a common origin, then every ray satisfies this condition. If I come down lower, I have a smaller angle and a smaller displacement, and the ratio is always going to be this radius of curvature. Does that make sense? So I can define the radius of curvature here for this family of rays in terms of the ratio of its displacement and its slope. Now I'm going to use the ABCD law. I presume I've got a curve mirror. They're all going to go down to some focus here. And of course, this is going to be this radius R2. And this R2 is going to depend on R2 and R2 prime. So let's compute those. So I know if I know R1 and R1 prime, I can figure out R2 and R2 prime. I know R2 equals A R1 plus B R1 prime. R2 prime equals C R1 plus D R1 prime, right? But the radius R2 equals R2 over R2 prime, and that equals A R1 plus B R1 prime divided by C R1 plus D R1 prime. Now I'm going to divide top and bottom by R1 prime. And so this becomes A R1 over R1 prime plus B over C R1 over R1 prime plus D. God, is this looking familiar? Now, then I go, oh my God, R1 over R1 prime, that's just the radius of curvature of my input ray. And so we finally get that R2 equals A R1 plus B over C R1 plus D. And this was the ray version of the ABCD law. And so, I always thought it was kind of magic how we got from Gaussian beams to the ABCD law. But there was some, family history here that kind of led it. So anyway, here's a relation between the radius of curvatures. Now, what's a lens ABCD? Well, the lens ABCD, if you remember, is 1, 0, minus 1 over f1. And my question was, what's the relation between these two radii? So R2 is going to be equal to AR1 plus 0 divided by R1 divided by F plus 1. Well, that's really enlightening. Doesn't help me much. If I invert it, it gets a little cleaner. So if I take the inverse of that, I'm going to get 1 over R2 equals minus R1 over F plus 1 divided by R1. Okay, and I can expand that. This becomes minus 1 over F plus 1 over R1. And there's a nice relation. So now what I find that 1 over R2 equals 1 over R1 minus 1 over F. So the focal length just basically subtracts from the inverse of the curvature. And so you can really quickly kind of figure out how to make these things work. So what if I have a focal length which is equal to the radius of curvature? Then my slope here is collimated. You know, so if I put this a focal length away from a point source, I have a collimated beam. You know, just like it should. So everything works out cool. But anyway, that was I always like this because it kind of shows you how you get from your ABCD matrix into this ratio of terms, which seems to have no business to go together. But when you realize, if I define my radius in terms of the ratios of these guys, then this ratio naturally evolves, and then everything falls out. So this is kind of, if you look in a classic optics book, you will find the ABCD law, and it's known in that form. So it's not with a Q, it's with the radius of curvature. Okay, did you follow that? Okay, that was easy. I've got one here. You won't like this one. So here's a cavity Q problem. Jeez. So we talked about the Q parameter. There's this another Q. So the quality factor Q. And the reason I'm mentioning this is because what you're going to learn about when you start talking about transients is something called Qswitching. Where Q is the cavity Q, which we talked about. So we had a Q, let's see if I can find that. Oh, crap. Here it is, okay. So our formula for Q was 2 pi d, the length of the cavity, divided by lambda, times R1, R2 to the 1/4 over 1 minus R1, R2 to the 1/2. Okay, let me see if I can kind of test this now. So I got a cavity, and we'll just put some mirrors here. And now I'm not going to worry about radius of curvature, but reflectivities. So let's say this has a reflectivity of 99%. And this has a reflectivity of 95%. And we'll give it a 10 centimeter length. Okay, so what's the cavity Q? So that's easy. Just plug the numbers in. Oh, and we need a wavelength. If in doubt, just assume 1 micron. Okay, so we can plug all the numbers in. 10 over 10 to the minus 4. You plug the numbers there. And you get, for this cavity, you get a Q of, it's 4.9 times 10 to the 6. Okay, big deal. Now, what would happen if I put a transparent medium in here, which has a transmission of 90%. So I'm going to add a loss to the cavity. And so I'm going to take away, only 90% of light gets through that thing. And this is how a Q-switch laser works. We're going to take a laser, and we're going to put a gain medium in it. And we're going to put a loss in there. And this loss is going to be so big that it suppresses lasing. And so you start pumping your laser and you build up this big inversion, a whole bunch of N2s, but it can't lase. So they just keep building them, more and more and more of them. And then suddenly you switch this to perfect transmission. And now the laser finds itself way above threshold. It's got lot more gain than it needs to laze. And so it just takes off like crazy, and like a, you get this kind of a exponential increase in intensity. You get this giant pulse. So it's a real neat way to get high power pulses out of a laser. It's called Qswitching. So this cavity Q parameter we talked about actually is something we'd come back and visit. So what's the Q of this cavity? How would you calculate the Q when I put that in? Any thoughts on that? So looking at these R's, especially something like that, what does that represent? Reflectivity is what? Imagine you got a blob of photons in the cavity. What does reflectivity tell you? Yeah?
How much energy is being, or how much energy is staying in the cavity?
Yeah. Per round trip, how much stays in? So you do a round trip, and R of it stayed in. And so I got a formula kind of like this. And what you do is I want you to kind of look at it. So you know what's really going on is I've got an R1, R2. So I've made a round trip, and I've R1 and R2 have remained. So if I add a loss in here, this is going to morph. And I just have to figure out what's remaining in the cavity. And what's remaining in the cavity is now R1, the transmission, R2, the transmission. So I'm gonna reflect, transmit, and get back to where I'm at. So the way to morph this thing, this is actually going to be an R1, R2, T squared kind of thing. And if I replace this pair by that, I'll get the right answer. Another way to think about this is, what if my cavity, instead of this, what if I had a cavity that looked like this? Ding, 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 ding. So I have a lot of mirrors. I wouldn't just have R1, R2. I'd go R1, R2, R3, R4. I have to hit every mirror to figure out how much is staying in the cavity. So this is like I'm going, 99%, 90%, 90%, 95, and then back and so forth. It's just like adding a couple more lossy mirrors. So in this case, though, it's not a mirror, it's a transmission. So think about this in terms of, well, my Q now is going to be affected because I'm going to retain less of the energy. So that's where the T squared kicks in. So I ended up putting in 0.9 squared in both of those and then recomputing my Q. So by adding a loss in the cavity, I'm just retaining less energy per pass. So if you do that, you get, for the second case, when I do this, I got a Q of about 1 million. So I have 5 times more energy with that out of there than I do when it's in. So the energy density in the cavity changes by about a factor of 5 by adding that loss. Which, I have 5% loss to 25% loss. Yeah, makes about sense. Yeah.
So it's R1, R2 to 1/4?
Yeah. Yeah, that's the 1/4, right. And it's 1/2 down here. Yeah.
Are we assuming that median doesn't reflect but instead absorb?
Yes, yeah, the total transmission is 90%. Some could be reflection. And yeah, so we're just assuming somehow 90% of light gets through it. So when we make a Q switch, you're going to put, we try and put something, often it's a Brewster cut. So it's like you put an acousto-optic wave with Brewster cut, so the reflections are 0. You just turn the acoustic wave off and it goes. Or sometimes you put actually absorbers inside the crystal itself, and they absorb, and then finally they saturate and they go away. So there's probably a dozen ways to make a Q switch. It's basically a shutter. It's just imagining opening the shutter in the cavity, then closing it again. Except you want to do it on a nanosecond scale. Yeah?
Do we just plug in R1, R2, T squared into the
Yeah.
equation over there?
Yeah, just put T squareds in those,
Okay.
and you'll get about 10 to the 6th. I just put this out. I just want to make you think about it. We learn these stupid formulas. This is not very enlightening. But we are going to talk about Q and cavity Qs and manipulate cavity Qs for purposes which make neat applications. You make a lot of money, in a company making these things. So they're commercial, interesting. But we're also going to, this is your very simple 2-mirror cavity. I want you to start thinking about what happens when I go beyond a 2-mirror cavity. What if I had 3 mirrors? How does this formula change? And so just start thinking about, well, okay, this is just, this is how much power is retained. And so I'm just going to add, I just have a big product of mirrors or whatever. And so this is So when I put a loss in here, I'm affecting how much power is retained. So I'm trying to get you to think physically what these stupid equations mean, and not just remember an equation. Yeah.
Those powers change if you add a T term in there?
The power changes in here dramatically. Oh, these powers.
Yeah,
These,
the power is one.
no. This is, I mean, again, we derived this for a 2-mirror cavity. If I had a 20-mirror cavity, I'd have R1, 2, 3, 4, 5. So this is just what's retained in the cavity. That's all it is.
Then it would be to the power of 1/4.
It'd be 1/4. Yeah. I forgot how we derived it. It came about. We got this by doing that line shape thing, and we were computing all the transmissions and taking square roots and stuff. So.
So in the homework there was something about so related to the photon lifetime,
Yes.
right? So what the formula for the photon lifetime? Because I've seen more than one formula for the photon.
There's a couple of them. Yeah. I've seen a couple formulas myself.
Yeah.
They give roughly the same answer. So the one I use is the one I can think of when I'm on that desert island. Because I spend a lot of time on this desert island, and I'm always trying to figure what are the damn laser equations here. So to me, I would have an R1 and an R2 and a blob of photons, and I'd say, okay, how many are going to stay in there? And so on a round trip, I'm going to have 1 minus R1, R2 retained. But if I put this stupid transmission filter in, I'm actually going to have, I'm going to start with them, I'm going to have T, TR2, T squared. So I would actually have that many photons retained after a round trip if I had that loss in the cavity. So I can accommodate kind of any perturbation on this cavity just by, once I know how to drive this thing. So as I add more elements, I know how to incorporate them in. So here I'd say, okay, after one round trip, this blob of photons is going to suffer loss twice in the transmission and once in each mirror. And that's my delta N. And then how long did it take? It was a round trip time, which is 2d over c. So my dn dt, if I divide that by 2d over c times my initial number, now I've got a differential equation. Now I've got a dn dt equals some constant times n, like this e to the minus, t over tau kind of thing. And my photon lifetime is going to be the reciprocal of that. But there's other ways to do it. You can do it in a more continuous. Some people will put instead of having discrete losses, they'll normalize the loss over the entire cavity, create an alpha, and do a logarithmic kind of thing. You get a slightly different answer, different looking form. It'll be within a few percent of the same number. So it depends on how you want to do it. There's not I guess, there's probably wrong ways to do it, but this is not wrong. And the other way is probably not wrong. Does that make sense? So I think it's really valuable to be able to kind of figure out not what the formula is, but how did you get there? What's the insight behind it? Could I have come up with that on my own? I couldn't have come up with ABCD law, but I can come up with things like this. So I always think in terms like that. What else? Okay, here's a mean one. So I've got a TEM01 mode. And it's a nice, I've got this mode. It's a nice big beam. It looks like that. And it's fairly well collimated. I'm going to run it through a lens. Of course, it's going to come to a focus. I'd like to know what's it look like here, and what's the diffraction angle? What's the diffraction angle for a 0-1 mode? After I've gone through the lens. Okay. So imagine I've got a nice big fat lens. I'm not worried about diffraction here, but afterwards. So how would I find that? So the way to get at this is if I want to know diffraction, I have to figure out what the spot size is there. Diffraction depends on my spot size because my diffraction angle is just 2 lambda over pi omega naught. So I've got to figure out omega naught. Nothing else to do. And I'm going through a lens, so omega naught's changed. I have some omega naught here, it's big, but I'm going through the lens, so it changes. So I've got to modify. So in this case, I've got to figure out the new spot size. Does that make sense? So you have to run the thing through the lens. How do we do this? I mean, let's just assume we've got basically a waist here. So Q1 is basically JZ naught, nice big collimated beam. So I want to propagate through this lens. And so what I'm going to do is just figure out what's Q2. So Q2 is just A Q1 plus B over C Q1 plus D. And for a lens, that's going to be Q1 plus minus 1 over F Q1 plus 1. Well, Q1 was JZ naught. So Q2 is going to be JZ naught over 1 minus J Z naught over focal length. And so what I'd like to do is break that into a real and imaginary term. And so you multiply by the complex conjugate, you separate the terms, and you get that this is equal to minus Z naught squared over F divided by 1 plus Z naught squared of F squared plus J Z naught over 1 plus Z naught squared over F squared. Okay, there's my new Q2. Okay, I'm done. Why am I done? Again, this tells me where the waist is. I don't care. I want to know how big the waist is. So I go to this term here. You know, it took me all of a minute and a half to calculate that. That's my new waist. The new waist, this is my new waist. This is my new Z naught. This is the new Z naught right there. And Z naught is pi omega naught squared. So I know that pi omega naught squared over lambda must equal this junk. So it equals my original Z naught divided by 1 plus Z naught squared over F squared. And so I now know omega naught equals the square root of all this junk here. You can do it yourself. So I now know the new spot size. I know the new spot size, so now I know the new diffraction angle. And I'm done. Now, this is a 0-1 mode. Does it have the same diffraction as a 0-0 mode? It's actually a bigger mode. You know, this is larger. My 0-1, my 0-0 looks about this big. This one's actually bigger. Does it have a different diffraction angle? Answer is no. The diffraction angle is this formula we've got, wherever I wrote it. I guess I erased it. Your diffraction angle, 2 lambda over pi, omega naught is universal. Omega naught is the size, it's a characteristic dimension for your beam. It's the radius for your 0-0. It does not necessarily represent a dimension on this thing. But this of course has a space of x e to the minus r squared over omega naught squared. So that's why it looks bigger, and it physically is bigger, but it's still characterized by that omega naught squared. So omega naught and z naught and all these things are just universal numbers which are connected to a beam. So you could come in with a really ridiculous, come in with a 10-10 beam. The biggest one I've ever seen is a 6-6. I think if maybe we generated a 5-5 once in the lab, and it was just absolutely gorgeous. And it was like a checkerboard. I mean, you could not use computer graphics to make a more beautiful periodic array. It's just awesome. It was just this very nice, bang, there it was. So you can generate these big beams. They all have the same diffraction angle as they would as if they were 0-0, even though they're large. So that's the downside. You get a bigger beam, you say, oh, a bigger beam won't diffract as much. No, it diffracts according to omega naught. How do I find omega naught? Just compute Z naught, you're done. All right? All right. Any questions? My last example is really trivial. I hope we ask something more intelligent than this, but it's just kind of a classic ABCD problem. let's say I have two lenses. What's the effective focal length of two lenses? So you're given an f1 and an f2, and they're separated by a distance L. What's the focal length of that combination as a function of L? Okay, so it's very easy to calculate. Let's just compute this as an ABCD, going from there to there. So again, you get out the old matrix machine, you grind this through. So first you're going to go through F1. Always remember the order. Then you're going to go distance L. Then you're going to go through F2. And then that'll get you through this thing. And you compute that and run it through. And this has a matrix 1 minus L over F1, 1 minus 1 over F, minus 1 over F2, plus L over F1, F2, and finally 1 minus L over F2. Okay, are we done? Yeah, we're almost there. Not quite. Yeah, but this gives you a pretty good clue. Sometimes you can look at that and say, okay, that's roughly my focal length. Because the 1 over F term will often give you that in that zone there. But a better way to do it, you say, okay, let's find out. And you might, if you're asked that question, you might ask, well, what do you mean? How do you define focal length? Where do you measure it from? If you actually do your optics, you'll find, if I take a lens, a physical lens, I define a focal length, I will define what are called principal planes. And my focal length is measured from that principal plane. And so this has principal planes somewhere. And so an optician would say, well, you want to measure F from the principal plane, right? So you might ask, what are you talking about? So let's just assume a focal length is measured from the end of this thing. So how do I find it? So the simplest way is to come in with parallel rays and see where they cross. So if I come in with parallel rays, they presumably will cross someplace. And that distance between here and there, that will be my focal length. Does that make sense? So just find a way to test it. So here's the ABCD matrix. So if I come in with R and 0, and I run it through that ABCD, I will get R2 and R2 prime. And this is R2, and this is R2 prime. And just as we did a minute ago, this distance from here to there is just going to be, that'll be the focal length in this case. F is just going to be R over R prime, or R2. So just using your, the sine of theta equals opposite over adjacent. And so all we have to do is say, well, let's just compute R2 and R2 prime, coming in with 0 slope, and that distance here, call it R1, and then take the ratio. And so you can do that real quick. So I got R2 was equal to 1 minus L over F1 R1. And I got R2 prime was equal to a whole bunch of junk here, minus 1 over F1 minus 1 over F2 plus L over F1 F2 times R1. If I take the ratio of that, I get the focal length. And so taking R2 over R2 prime and simplifying a bit, I got a simpler somewhere here.
That's for a ray that's coming in parallel, right?
They came in parallel. Yeah, that's why that's a 0. Yeah. And oh, here it is. Okay. I got for final answer F2 L minus F1 divided by f1 plus f2 minus L. Okay, so that's how you can figure out the focal length, real quick and easy. So you know, you're just using the ABCD laws and your head. You say, okay, I'll come in parallel. That creates a focus. You got to know that fact, and then from that you can very quickly say, okay, I'll figure out where they cross, and there you go. So with this, you can compute all sorts of crazy things. Yeah.
I thought R2 over R2 prime, that was for the radius of curvature.
Yeah, it's the radius of curvature, but it's just it's the same thing. They're converging to a point, and so you do have a radius of curvature here. You know, all these guys are going to be descending right to there. So in this case, it's the same thing. Yeah, the radius curvature. Yeah, the focal length and the radius curvature are equal. Remember that formula? It was 1 over r1 equals 1 over r2 minus 1 over f. This is planar, so that's 0, or that's 0. The radius curvature, yeah, so 0 equals that minus that, so r2 equals f. Yeah, so it works. All right. So I was just trying to come up with some dumb examples of how to apply things we've learned. You know, we've taught you ABCD, cavity Q, the Q parameter, the Gaussian beam. I've been trying to think kind of problems. I don't know what I'd ask, but you know, the best way to study for this is just think, well, what would I ask? And, you know, give yourself a little self-test. You know, do you understand the complex beam parameter? Do you understand Gaussian beams? You know, could I derive the ABCD matrix for a curved dielectric interface? You know, just that kind of stuff. Just these little simple examples, and go for it. Yeah.
How deeply can we be tested on chapter 1?
Yeah, I don't know. I mean, that's a tough one because it's, you know, coherence and that kind of stuff. I never know how to ask a good question. And Sandip's a smart. I mean, Devdeep's a really bright guy. I was really enjoying his lecture because he has a lot of insight. You know, he shows you how the dispersion equation relates to stuff. That's neat stuff. So he'll be more into that stuff than I am capable of being. So I don't know. There might be a good coherence question. That's a good thing to think about. What would you ask yourself about coherence? What's the question you would dread about coherence? You know, and what that'll do is it'll expose the raw spots in your knowledge. You know, the wave equation, that kind of stuff. I don't think we're going to go too deep into that. But you know, uncertainty. You know, you should be a little bit. There's an uncertainty principle. You know, we keep seeing that. So have some sense of when that applies. Yeah.
Does the homework cover, like, does the homework that we've done so far cover, like, basically all the topics?
Yeah, as far as I know. Yeah. So, yeah.
Do you know if we're going to be allowed a formula sheet?
I don't. He sent an email, didn't he?
It's open book.
Open. Oh, that's the worst kind. Yeah. Okay. So you're. Those are brutal. So, yeah.
There's a question on the prelim asked to optimize the FSR
Optimize an FSR.
for two pretty similar frequencies coming in, but you only want one to transmit, so you use the I forget the word for it, but use the filter thing.
Yeah.
And yeah, so what would be an optimal FSR?
So you got two frequencies coming in,
And they're pretty similar.
and with one cavity, you want one to transmit and one to block.
Yeah.
You know, I don't know. Just I guess I'd say. I mean, the optimal. I'd want the transmission. I got this thing like this. I'd want one transmitting here, and I want one right there in the middle. That'd be the maximum rejection and the maximum transmission.
Oh, okay.
So that's what I'd look for. So here, you know, you just set one frequency to Q times FSR, another to Q plus Q and a half times that FSR.
So FSR is not in any of the chapters, I think, of the book.
Oh yeah, yeah,
Is it?
It's chapter 6. What? It's chapter 6.
yeah. We talked about it's the resonant cavity. So we talked about the frequency of the modes, and so the FSR was the C over 2L term between the. We took a plane mirror cavity, and you calculated what the resonance of that cavity was. We found all these various frequencies, and they're all separated by C over 2L. That's the FSR. So, yeah. Yeah, that FSR would be a good question. Finesse, those are good questions, yeah. Okay, well, good luck. I won't be here Friday, so I'll be thinking of you, but.